Hello. In this video I will be presenting our research paper titled Unexplored Phases of Robustness and Out of Distribution. Covariate Shifts in Environment and Sensor Domains. These days, DNN models are widely used in various applications ranging from face recognition to autonomous vehicles. However, DNN models often does not perform as expected when the environment changes from the training environment. The main reason behind this is known to be domain shift. There were numerous approaches to overcome the domain shift. These include out-of-distribution detection or domain adaptation and generalization. All of them tries to make a smarter DNN model, but is it the best? Let's see how we deal with such a case. When a person cannot see well because of the environment or eyesight problem, what is your advice? Do you advise to read more books to be smarter? Maybe not. Instead, you recommend them to wear sunglasses or proper glasses. In computer vision system, sensors serve as the eyes, and DNN model plays the brain role. Previous approaches focused on the model, but not on improving the image acquisition process. But as we humans do, we need to pay more attention to eyes part. To this end, we collected a new dataset, ImageNet-ES, which covers the rather unexplored part, environment and sensor domain. To systematically collect the images with perturbations in environment and sensor domain, we constructed a new testbed, ES Studio. With thoughtful design, we could not only capture real-world perturbations related to light and camera parameters, but also ensure reproducibility. Using ES Studio, we collected a novel dataset, ImageNet-ES. ImageNet-ES consists of images with variations in light and camera parameters and includes total 202,000 images. This figure shows the sample images from ImageNet-ES testset. You can easily see how the images look different under various light and camera parameter settings. Now our experimental results are presented. Firstly, we did experiments on out-of-distribution detection. We reinvestigated whether the most widely used semantic-centric framework still works well with ImageNet-ES. To investigate, we calculated the distribution of OOD scores from EfficientNet for 3 techniques on 3 datasets. The OOD scores from in-distribution and SOOD are clearly separated for all 3 methods. The OOD scores of ImageNet-ES, however, is spread across the entire spectrum. This implies that under semantic-centric framework, the existing methods might not distinguish COOD data very well. We also considered model-specific OOD framework. Under this framework, OODs are defined by whether the model correctly classified the image. We conducted similar experiments to semantic-centric framework. The state-of-the-art method, VIM, can separate ID plus and minus, but still cannot distinguish ImageNet-ES plus and minus. On the other hand, MSP shows clear separation between ImageNet-ES plus and minus. Another experiment was executed to evaluate various OOD detection methods on ImageNet-ES. This chart illustrates the OOD score of each parameter setting and corresponding classification accuracy. We could observe that classical methods show more desirable correlation, while VIM accepts numerous samples as ID which are misclassified by the model. Overall, extensive experiments with ImageNet-ES implies that no single method is superior in both COOD and SOOD detection. To explore how to enhance the robustness in the environmental and sensor domain, we fine-tuned ResNet 50 model using various domain generalization techniques. They include basic and advanced digital augmentation, and mixing real-world perturbed data during fine-tuning. Digital augmentation improves the robustness on ImageNet-C, but not on ImageNet-ES. On the other hand, including ImageNet-ES for fine-tuning improves the robustness on both digitally or real-world corrupted images. We also evaluated various models on ImageNet-ES. The results indicate that well-tuned parameter setting could greatly improve the model performance. Moreover, even very light model with best parameter setting outperforms much larger model with auto exposure setting. This highlights the importance of sensor parameter control. The qualitative analysis on ImageNet-ES reveals that model may prefer images that do not look great on human eyes. This implies that sensor control should prioritize features based on model's perspective. To conclude, we investigated distribution shifts resulting from perturbations in environmental and sensor domains. To this end, we constructed ES Studio and collected a novel dataset ImageNet-ES. With ImageNet-ES, we conducted comprehensive studies in OOD detection, domain generalization and sensor parameter control. Our future work would be to improve ES Studio to take photos of real objects or printed photos, rather than capturing display. Thank you very much for your attention.